your system order closed loop becomes a third order system. And third order system, typically, what kind of problem you will face? Instability. Okay, instability. So you must know, right? It will actually work around with the instability. Also, because of a third order system, using a PID, we did mention PID plays a pole in a forward loop. Okay, it also plays two zeros. And the 2-0 we have seen before, the 2-0 actually stay put. Right? The thing about your 0 in your closed loop transfer function in your system is if you have any 0 in the forward loop, that zeros will stay put in the closed loop. That's what we discussed the last part of the last week lecture. And that is important because when you have a 0 you place into your closed loop system, what happens is you need to be careful with the overshoot, depending upon the 0 location relative to your complex conjugate pose. So if you have a complex conjugate pose, that means you have a system, basically you already under them, the 0 will basically aggravate the effect of overshoot, but at the same time, the 0 actually speed up the response. Alright, the downside of course, I mean, that is a downside that overshoot becomes very high. Okay, good thing, the response actually becomes faster. And all that, as what we have discussed so far, we also conclude that that will only affect during your transient, right? Because in a way, the derivative control action is only effective during the transient. Okay? Alright. So now we will go to the next topic. Okay, so it's for everyone because now you need to go on to take a look on your root locus also. Okay, so today we will start your root locus analysis. We will look at your system definition, basis of the techniques of sketching a root locus, technique for sketching a root locus, damping ratio, and the root locus. Okay, so you can imagine all these are important things. Okay, one thing is you have to get it correct. Okay, in a way, if you look at all the past year papers, so if you have the time, I guess all you need to do is you don't go too far back. Okay, so all you need to do is to look at 1-4 August, 1-4 May, and 1-3 May, and 1-3 August. That should be all that sufficient if you need to practice. Okay, if you need to practice during the last phase and all this and that, and then you more or less you can work it out as a question that you'll be working on. Okay, but typically you can see that the way the questions actually being asked quite similar, right? I mean, we'll be basically touching on all this. So one thing also you do take note is, okay, if you look at the past year, I've been raising this with them, but somehow they were sticking, they were not budge, but they basically, I mean, they do know, right? Typically, if you are asked to identify the open loop poles and zeros, okay, so it depends on the system. So sometimes you need to write down a couple of poles and 1 zeros, or then at the end of the day, how many poles more than a zero, and so on. Information of such for Glasgow normally they give 1 mark. Okay, so that is why I have a problem because I don't give half a mark. So you either get it or you get 0. Okay, so I mean I've been asking them, maybe can you increase it to 2 marks at least? You know, you get partially correct, you get 1 mark. No, they always is either 0 or 1. Alright, so it's quite straightforward for them, 0 or 1. So that is why I say you have to be very careful. It's very straightforward because you aren't given all the information. All you need to do is you repeat the information, you write it down, how many open loop poles, location of the open loop poles, how many zeros, no zeros, then what is the number of poles more than the zeros, and so on. Such information is only 1 mark. Okay, so if you were to make a mistake there, I will tell you, if you make 1 mistake, I can close one eye, still give you the 1 mark. But if you make 2 out of the 3-4 things that asked for, then you get 0. Okay, so I mean, then when you look at a paper, don't come back and ask for marks and all that. Okay, all right. So that is what I say. You have to be careful when you answer the questions of this root locus analysis. Okay, root locus is actually a time domain technique. You use it. We can actually use it for design purpose. Okay, because this is an introductory course, so we don't basically cover how to do it for design purpose. But what happened here is with the root locus in the analysis, we are also exposing you to a very simple basic proportional controller. So you use it for proportional controller design, it is actually possible. Okay, it is actually possible you use the root locus technique because you can actually use it to do your PID controller design. You can also use it to do your lead lag compensator design. I think some of you have learned it in your poly days that you still remember. But in this Dynamics and Control 3S, we will only be touching on, at most, your P controller. Okay, we will not be basically going into how to actually do a lead lag compensator design and so on. Okay, all right. Let's take a look at all the basics. So this is how the root locus is going to look like. This is actually generated using MATLAB. So MATLAB is actually quite straightforward. RLO, CUS, numerator polynomial, denominator polynomial. You key it in. This is what you will generate. So the notation and all that still keep to what we have actually covered. Similar to what we have talked about in your complex S-plane. You see across, it has to be a pole. Okay, and then you see zeros, they are circled, they are basically representing zeros. So in this case here, you have two poles, complex conjugate poles in the complex plane, and you have two zeros on the real axis and so on. Okay, so only thing that your MATLAB will not indicate will be the direction of the pole movement. Okay, so that is something that you need to do in exam. So that is also something that I found has been missing in a lot of students when you do it in exam. Okay, a complete root locus, primarily you need to indicate the pole movement. Basically, the pole movement correlates with increasing your gain K. Okay, because in this root locus, when we are plotting the root locus, we are assuming that there is a gain K. And this gain K basically will be increasing from a small value to a very large value. Okay, so when you draw the root locus of such, you need to indicate, you need to tell me that which direction is actually moving. Okay, in this case here, I'll try. I never use this. So in this case, we do know that. Okay, all right. So basically, if you were to sketch it, a typical root locus, you started out from your pole, and you do know that when you increase the gain K, this is what's going to happen. The pole is going to be moving towards each other, and because what happened here is, if the pole is going to be breaking out or it's going to be going into the real axis, it can only happen at a point that is actually you have a repeated roots. Okay, so one thing you need to take note is it has to be a place where you have a repeated roots, then you can actually break it out into your complex plane or from the complex plane onto your real axis. So in this case here, you have two zeros. So what happened here is the pole will be moving towards the real axis, and it will actually at this point, okay, at this point here, right, it will basically, you have a repeated roots, and then from there, one will move to the right, one will move to the left, okay, approaching the zero. So this is something like what the AE student has studied, right? You study your fluid mechanics, your aerodynamics, source and sink. Source will always want to go to the sink, right? It's a standard thing, okay? Don't ask me why, but you really study your fluid flow and so on. So that is a standard thing. That for your root locus is the same thing. The pole will always approach the zero. Okay, so what we will go through bit by bit is to basically guide you through. Okay, some of them basically, some of the technique here basically presented a lot of things which I think I don't use all of them. Okay, but some of the things that I use, I will basically let you know. Okay, going back to what we have discussed, we assume that we have a closed loop transfer function. Okay, this closed loop transfer function is GCS, so it's actually given you have an output function over your input function. So this can be anything arbitrary. So I mean, you don't have to call it CS over RS. So you can also call it XOS over XIS, output over input. And basically, we do know that the transfer function basically consists of numerator polynomial, denominator polynomial, PS and NS. Alright? Agreed? So this is basically day one that we talk about this. Okay? So both your numerator and denominators are polynomials function of S. That means it's a complex function because your S can be sigma plus minus J omega D. Right? Where your sigma is your Z omega N, omega D is omega N multiplied by square root of 1 minus sigma squared. So that is basically it's a complex value function. So in a way, if you were to take a look here, what will be your closed loop zero? The closed loop zero of the system basically obtained when you set the numerator equal to 0. Numerator polynomial. You set it equal to 0, you get your closed loop 0. Agree? Okay? Alright. So what are your closed loop poles then? Your closed loop poles, of course, is the same thing we obtain from your characteristic equation. Characteristic equation, primarily, you set your denominator polynomial equal to 0. Okay, and then you solve for the roots of your characteristic equation, and that basically will give us your closed loop poles. Okay, one thing about your root locus is root locus basically enable you to work out the solution of this QS equal to 0 when you have a parameter K that is actually changing in your block diagram without actually calculating it. Okay, so we will see how we can actually do that. So this is a characteristic equation as what we have repeated many times. Solution giving the closed loop poles of the system. Okay, so if you set this equal to 0, basically you work out the closed loop poles. And of course, we emphasize this many times. What does your closed loop pole do for you? It determines your characteristic of the response, right? Your dynamic characteristic of the response of the system. At the same time, stability. Okay, stability is very important. Whether your closed loop system is stable, unstable, primarily determined on the pole location of your closed loop system. So the poles in the left half plane, no problem. Closed loop system basically will be stable. The moment the poles move to the right half plane, then your closed loop system basically is unstable. That's what we have discussed before using your PID controller, right? PID controller or your PI controller, we did mention that because both actually increasing your system order by 1 and at the same time run into a possibility of instability. Okay? Alright, so bear in mind how your closed loop poles is going to be affecting your performance. Okay? Characteristic response of the system basically also determine the performance. Right? Your rise time, peak time, maximum overshoot, settling time and all that, all determined by this characteristic response of the system. Okay, and also again is basically the pole location. So that is what we have discussed before. You have this S-plane in the root locus. We do know that anything in the open left half plane, your response will be stable. Anything on the open right half plane, your response will be unstable. And of course, the J omega axis is what we call marginally stable boundary. That means when your system is stable, crossing into instability, you need to pass through this J omega axis. And we basically, you can use the root locus method to determine this point, right? Because using the root Hurwitz, how do we do it using the root Hurwitz? All you need to do is, based on the K value, you work it out. One of the first column element, you set it equal to 0. That basically will enable us to work out what will be the stability boundary. Am I correct to say that? If you have a standard like you have a standard transfer function that looks something like this, right? Say for example you have this s cubed plus 3 2s squared plus 4s plus k equal to 0. Then Okay, you do know that k has to be greater than 0. I mean, this basically just hypothetically just work it out. So you get k minus 8. So what happened here is from this root table, you can actually see that if this element is going to be equal to 0, okay, you basically go into its stability or stability boundary, because when k is equal to 8, this element basically is equal to 0. Correct? And we do know that basically stability you base on above and below, because this is positive, k is equal to 8, this is also positive. So if this k is equal to 8, what happened? This element equal to 0, on top, below, same sign, you have a pair of complex conjugate poles on the J omega axis. Okay, so that was what we discussed when we were looking at your root Lewis stability criteria. Can you follow that? Okay with that? Okay, so we discussed about this. Okay, we discussed about this when k is equal to, we said, right, k equal to 8. This is basically marginally stable. Okay, why? Because when k is equal to 8, this element is going to be equal to 0. So it will be the first element in a row that is actually equal to 0 based on what we have discussed in the analysis. We work it out. So this one, I'll leave it to you. You can actually go back and play around with it. Okay? Alright, so the important thing is you can actually use a root weight, but we can also do it using your root locus method. That's what I'm saying. So you can imagine that when you go into the exam, it's not only one method to work out the answer. There are many different ways of getting the answer. Okay? Alright, it's just like for your guys, right? I mean, NS time you went through jungle training, right? There are many ways of killing a chicken, right? Right? You're killing the chicken, you're killing the pythons and all that. So that's what you learned before. So same thing. Here we don't teach you only one method, there are many different methods. Okay. So coming back to the closed loop. Okay. Alright. As the gains are variable, as we mentioned before. Because why? Because we were talking about this root locus gain. So are the coefficient of the polynomial, because you do know that when you have if you have a transfer function, alright, if you have a transfer function that you have a variable gain, then what happens here is when you change a k, this polynomial will change, okay, and as a result that this polynomial basically when you change, what we are saying here is something like this. Okay, so in your closed loop transfer function, you have k over s cubed plus 2s squared plus 4s plus k. Okay, and what we are saying here is if I have to change a k value, right, and increase k. So what happened here is you can actually see that your characteristic equation is s cubed plus 2s squared plus 4s plus k equal to 0. Every time you change this, your characteristic equation has changed. So if you were to try to find the roots, you can basically see that your closed loop poles are actually shifting. Okay, so if you were to do it, if you don't use a root locus method, if we were to ask you to determine the closed loop poles and all that, so you need to basically keep putting in different k value and then you solve it. I mean, of course, you can actually do that in MATLAB quite easily, right? I mean, you have learned how to use MATLAB to do all this, so it can be done quite easily, but if you were to do it by hand, it's going to be a chore, okay? Alright, so that's what we say. So that's their position in the S-plane. As the gate is varying from 0 to infinity, the closed loop poles will move around the S-plane. And what happened here is the path that they trace out is what we call the root locus. Okay, what we call the root locus. So if we go back to this, okay, if I have to redraw, so this one is going to be s squared. So you'll be s squared. So this is s squared plus 2s plus 4. So what does multiply. Okay, so this is actually 0, this is actually minus 2, minus 2. And what I'm saying is, if I can change a k value without doing the calculation, I can show you that one of the pole is going to be moving this direction, the other two is going to be moving this direction, and then it's going to break up and it's going to go into the right half plane. Okay, so this is basically what we meant. K increase, K increase. Okay, so the few sentences down there, you know, all the thing that they're talking about and all this and that, primarily is trying to tell you that if I have this, okay, the wordy things that this guy is trying to explain is, if I have a system, imagine that I have a root locus k, right? And this k can actually change from 0 to infinity. Okay, so what happened here is, from this is my system transfer function. I can actually work it out. I can actually plot all this in the S-plane, complex S-plane. And I can actually plot it in such a way that I can actually show you how the closed loop pole is going to be moving without actually solving the characteristic equation. Because when you do work it out, this is a characteristic equation. S cubed plus 2s squared plus 4s plus k is equal to 0 is a closed loop characteristic equation. If I change a k value, what happens is when I change a k value, your polynomial will change. And then when you find the roots, the root will change. Okay? So here is basically a solution to this with the k being changing. The k change, because when the moment the k change, your characteristic equation will change. Okay? So you started out, okay, you put k is equal to 1, s cubed plus 2s squared plus 4s plus 1 is equal to 0. You solve it, you get one set of solution. You put k is equal to 10, become s cubed plus 2s squared plus 4s plus 10 equal to 0. Your characteristic equation has changed. So you can actually see that your characteristic equation are basically what we call increasing. Okay? They are basically increasing. You were looking, this is from the denominator. Characteristic equation is only the denominator polynomial. Numerator, of course, is also changing. But what we are interested in your root locus plot, we are only interested in the characteristic equation. Denominator polynomial. Because we say your denominator polynomial, basically, when you work it out, is your characteristic equation. You solve for the roots, that will give you your closed loop poles, because your closed loop poles give us two things. Your closed loop poles give us your characteristic of your dynamic performance, right? Your response, step response, and also stability. So in this case here, you do see that the pole will basically move into the right half plane. Okay? Into the right half plane. And I can show you later on, as what I mentioned many times before, we talk about your second order system and third order system. Why second order system? You're not so afraid of instability, okay? Because once you learn the root locus, I can actually show you quite easily. Whereas third order system, without fail, you will run into instability problem if you are not careful. Okay, so that's what we mentioned before, right? When we talk about your stability analysis and all that. Okay, all right. Any question? Any question? So this diagram basically explains what this guy was trying to say. Okay, I mean, if you read this, it's very long-winded, right? Okay, so all this from this actually extracted from your reading material for section 7. So all this can actually be summarized by telling you, I have this system, I have this gain k. K can actually change. K is a variable. Okay, I can tell you that k here is a variable. Okay, so k is actually a changing parameter. And of course, with the k, I can actually form the closed loop characteristic equation. And from the closed loop characteristic equation, by changing the k value, I actually obtain different characteristic equation. And at the same time, eventually, when I work it out, you get different closed loop poles. Okay? And all this can actually be worked out using what we call the root locus plot. And that's what the lecture material basically say that if you change the k value at different k value, so this is actually increasing value. So if you were to take a look here, you can basically say that this point is basically k equal to 0. This point is also k equal to 0. And then when k is not equal to 0, you work it out, you move. Okay? Alright? Okay? Okay, a very, very simple way of looking at all this. Okay, I mean, maybe I explain it this way, you will see it much easier. Okay, so this is what? This is your system. So, as we mentioned, this is your plant. Plant being represented by ns divided by ds. Of course, when you set ns equal to 0, what do you get? Your open loop 0. Alright? Okay? When you set your ds equal to 0, what do you get? You get your open loop poles. Okay? So you can actually work it out, the closed loop equation, transfer function and all that, but what we are interested in, as what we mentioned, your characteristic equation. What is your characteristic equation? Your characteristic equation is going to be equal to 1 plus k multiplied by ns divided by ds is equal to 0. Okay? And of course, you can actually write it as ds plus k ns equal to 0, and we basically say that we start from k equal to 0, right? When you do your root locus, you start from k equal to 0. So when k is equal to 0, what do you get? You get ds is equal to 0. Alright, from this equation here. Okay, so you say, okay, ds is equal to 0. That means where do you start your root locus? A very simple way, you start your root locus from your open loop pole. Alright? Alright, because it's ds is equal to 0. Then we say, okay, in your root locus, you say k equal to 0, then eventually k goes to infinity. Okay, coming back to this is your characteristic equation. So in your characteristic equation, what happened here is you have to rewrite your equation. So what happened here is if you do this, okay, when k approaches infinity, this term drop out, so you ended up with ns equal to 0, or rather ns equal to 0. So ns equal to 0 is what? Your open loop 0. So in a very simple term, you say that to plot your root locus, that is why you need your open loop poles and your open loop zeros. Okay? Alright, so bear in mind, to plot your root locus, the very important thing you need open loop poles and your open loop 0. Okay, next question coming back. But my transfer function, if I look at my transfer function, if I have 3 poles and then I have no zeros, then how can it be from open loop poles to open loop 0? Okay, so think about it. So what we did mention before, we mentioned your 0, if you still can recall from the very second lecture we discussed this, your 0, you have your finite 0, you also have your infinite 0. Am I correct? We mentioned before, if you have a transfer function, you can actually work out what is your finite and what is your finite and what are your infinite 0. Okay, that means if you have a transfer function of this, based on the 0 definition, okay, so you have s plus 1, so this is s plus 2, s plus 3, s plus 4. Okay, in this case here, I have 3 open loop poles, but I only have 1 open loop finite zeros. Okay, we mentioned how to actually work out the infinite 0. What about the rest of the 0? The rest of the 0 are basically what we call infinite 0, because if you remember, what is the definition that basically will make your what is the zero definition? The definition for zero is the point's going to make your transfer function goes to zero. GS going to zero. That basically, that particular point is going to be your zero of the transfer function. So in this case here, we say if I can actually accept s equal to infinity. Okay, so if I accept s is equal to infinity, you can actually see that g infinity, this is going to be, so this will be basically infinity and then divided by, this are 4 infinity, so infinity to the power of 4. So very simply, you can actually see that basically this will also go to 0. Alright, because why? Because if you were to look at this, this is basically what? If you were to allow infinity in, so this is 1 divided approximately s to the power of 2. Alright? Because you can actually cancel out one term, because when s gets very large, you don't have to worry about what is behind. So you only concerned with, you can actually write it as when g infinity, right, when s is actually set at infinity, g infinity is approximately equal to 1 divided by s squared. But if s is equal to infinity, this will basically go to 0, and it actually fulfill your 0 definition. And that is why we say that for a transfer function of such, okay, we mentioned before, you have 3 open loop poles, 1 open loop finite 0, and 2 open loop infinite 0. Okay, so at the end of the day, basically in the root locus plot later on, you will see that that is why it makes sense. When we come back to talk about this, you have open loop poles, and open loop poles will go to open loop zeros. So it depends on the transfer function. If your transfer function has 1 finite 0 and 3 open loop finite poles, and as we mentioned, pole has to go to 0, then what happens to the 2 poles? One pole can go to the 0, the other two poles have to approach what we call the infinite zeros. Okay, and that is how we will introduce along which direction these 2 poles are going to be approaching your infinite zeros. Okay, your infinite zeros, your open loop infinite zeros. Okay, so there is a direction that the pole will basically be approaching. Okay, alright, so the important concept here is this open loop poles and open loop finite zeros and so on. So typically what happened here is you do see that sometimes they use the, I think later on, okay, I mean when we come to the lecture part and I'll show it to you, basically you need to indicate what is the number of poles, what is the number of zeros, and the other thing that they will also ask you to indicate is the number of finite poles minus the number of finite zeros, and they use the term n, and that n basically in a way indicating the number of infinite zeros. Okay, I'll see where is it in this, we'll take a look later on in this lecture materials here even. Okay, alright, so this is basically the root locus that we are looking at. Okay, let's take a look of this work example. Okay, you have a mass of 2 kilograms. Okay, supported by a spring of stiffness 100 Newton per meter and a damper with coefficient 40 Newton second per meter. You have a force P is actually applied to position the mass in the required location RT. Okay, while the instantaneous position of the mass is actually given by xt. So the force PT is actually proportional to the error between the required and the actual position of the mass. And the constant of proportionality in this case here being your Kp. Okay, so this is a rather long thing. So what happened here is we were asked to try to find out, okay, we were asked to try to find out, to draw the block diagram and so on and so forth. Okay, so going back to this, if we were to take a look of the block diagram, we do know that based on the applied force, right, you were given the applied force and then you have the position, instantaneous acceleration of motion of the mass is going to be equal to what? Mx double dot plus Cx dot plus Kx is equal to P, right? Or Pt. So this actually is xt, or you can actually just drop it, right? Okay. So if we were to take Laplace transform, assuming zero initial condition, of course, I can actually write it as such. Okay, in the questions we are also given that the instantaneous position of the mass is given by xt. The required position, okay, there's a required location rt, and then what happened here is the force pt is proportional to the error between the required and the actual position. That means if I have to draw the free body diagram, this will look something like this, right? You have, because it's RT given, so I put it in Laplace transform RS. So this is positive, this will be basically your XT. So this will be your XS. So coming out here is going to be RS minus XS. And it's going to be going through what you call proportionality, right? Constant of proportionality before it is actually driving your PS. Alright, so this is your ES, actuating error signal. Okay, so we were given this information. PS is going to be equal to KP multiplied by RS minus your XS. So as a result, if I have to combine the two will look something like this, right? So this will be 1 divided by ms squared plus cs plus k, and then this is your xs, and this is your rs. So you were given that m is equal to 2 kilogram, and then your c is equal to 40 Newton per meter, Newton second per meter, and then k, your k is stiffness is 100 Newton per meter. Okay, so what happened here is, of course, you need to work out your closed loop transfer function. Okay, your closed loop transfer function is going to be Kp divided by ms squared plus cs plus k plus kp. Okay, so this is going to be equal to Kp divided by 2s squared plus 40s plus 100 plus kp. Okay, alright. So now, going back, this is what they were asked to do. Alright, calculate the pose of the system and comment on the stability and expected response characteristic when Kp takes the following value. So the Kp can actually take from a negative to a positive value, right? Minus 142, minus 100, 0, 28, 100, 150, 172. So what does it look like? Let's take a look. So what happened here is, if you were to take a look of Kp is equal to minus 142. So what happened here is you have two poles because it's a second order transfer function, right? Because this is exactly what we did. Okay, you have a Kp here. So this, you set it equal to 0 is your characteristic equation. So in this case here, what is our characteristic equation? Is 2s squared plus 40s plus 100 plus Kp equal to 0. So that's your characteristic equation. So the question basically saying that now I put Kp is equal to minus 142, minus 100, 0, 28, 100, 150, and try to solve it. I just realized, hey, how come this one is 100? This should not be 100. This should be what? This should be 100, 150, 172. Okay, so this should be 172. Never mind, I'll go back, I'll change it. Okay, but nevertheless, you do know that what happened, these are the values that you need to actually put it in to solve it. And basically what happened here is, if you were to take a look, you're starting out when it is minus 142, you have one pole at minus 21, you have a pole at 1. So what happened here? You have a pole in the right half plane. System unstable, exponentially increasing response. When Kp is equal to minus 100, you have a pole 0, you have a pole at minus 20. So 0 at 0 and minus 20. So what happened here is you have a marginally stable pole, because this is 0 is marginally stable, and then this is basically stable also, minus 20. So this is a case where you have a pole that is actually stable, you have one that is actually marginally stable. So in this case here, your response can actually be exponentially increasing depending upon what kind of input that you put into the system. Okay, it depends on what kind of system input you put it into the system. If it is unstable, then it's going to be exponentially increasing. Okay, so that is actually possible. When you set Kp is equal to 0, you have minus 17.1 minus 2.9. So what happened here is your response will be stable, right? Because two poles are in the left half plane now. So you are at this minus 17.1 minus 2.9. So you can actually see that your response is going to be what? Exponentially decrease. I mean, it's going to be exponentially decreasing. Okay, exponentially decreasing, meaning in the way that the response basically will be not exponentially decreasing. In the way it's like if you have a step input, so it's going to be like a step response. Two first order steps superposition onto each other. Okay, so if you have a pole at minus 17.1, minus 2.9, so if you were to ask how would the response look like, it all depends on the transfer function that you have, but typically you can actually think of it because you have a pole at minus 17.1, so you have a pole at minus 17.1, you have a pole at minus 2.9. So if you were to take a look at the step response basically will be 2 first order. So this is first order. This is also first order. So for a second order system, what happened here is you just add. Okay? Add, that means you superimpose onto each other. You add it onto each other. And that will be the end result. So if that is the case, if that is the case, then you actually get something like this. Okay? So that is basically the step response. Okay? So you can see that coming back to this, when you increase the K value, you have a point where Kp is equal to 100. You have two poles at the same location. Two poles at the same location as what we discussed in your second order system. You have a stable critically damped, right? Because why? Because you have a repeated roots. You have a pair of repeated roots, repeated real roots. That means your damping is actually equal to 1. In this case here, your damping is actually equal to 1. So at this point here, when Kp is equal to minus 10, so this is zeta is equal to 1. Okay, so that is a point where your zeta is equal to 1. Okay, that's what we call critically damped. Then beyond that, if you keep increasing the gain, so what happens here is becomes stable oscillatory. Okay, it becomes stable oscillatory. So this is basically stable exponentially decreasing. All right, this should be decreasing. But in a way, if you were to look at the actual step, this is the actual step response that you can actually imagine, right? Actual step. So you basically have two first order. So first order response basically looks something like this. When you have a system, we have two first order pole characterized by two first order pole. The end result is you add the two together, and you get your final step response. Okay. finally can actually trace out all the dots, because you will have so many dots on the real axis and into the complex plane, and eventually it looks like what we discussed before, your root locus. So your root locus primarily is if you were to combine all those points and then you plot it, make it finer and finer, and this is what we mentioned before, right? I mean, this is your root locus. Okay, so this is a case where you no longer use point by point to indicate. You just draw a straight line. Okay, you just draw a straight line, because this straight line representing many points on in the complex S plane. Okay, when it traces it out, so this in a way that if you were to say that, okay, if you have to work it out, it basically is something like this: point by point, point by point, point by point, point by point in your complex S plane. Okay, but because the points are so many and they are so fine, they are very close to each other, you just draw a straight line to represent them. So that is what we talk about. Your root locus is going to look like. Okay? Alright? Yes?
So most of the time you just draw the branching line out.
Yes, you just draw the path, you don't indicate the point anymore. Okay? Yeah. In exam also they cannot ask you to do it because you don't have the software. So third order you cannot calculate. You only can calculate second order. Alright? I mean, unless you can do third order polynomial, so that means you are much better. I can only do second order. Okay? Alright, so back to what we have. Look at, so this is the case, right? If you do it single point by point. Okay, so now coming back to this closed loop system again. Okay, so a bit of the system definition. So this is your closed loop transfer function, GCS. In this case here, GCS is going to be equal to CS divided by RS in a way based on your GS and your HS. So you have your GS is a for loop block, HS is a feedback loop block. Okay, when you work it out, what will be your characteristic equation? 1 plus GS HS equal to 0. So characteristic equation is going to be governed by 1 plus GS HS equal to 0. What is your open loop transfer function? What is the open loop transfer function? Can someone tell me? What is the open loop transfer function? Can you still remember? GS HS, right? Open loop transfer function, that is the GS HS. So your closed loop poles are obtained from the solution of this characteristic equation. Closed loop 0 are obtained from GS is equal to 0. We have seen this previously. Okay, as we mentioned before, if you have any 0 in the forward path, it will always end up as a closed loop 0. Okay, the other thing is we mentioned if you have a pole in the feedback HS, it will also end up as a closed loop 0. Okay, but nevertheless, in this case here, I guess the assumption is you will not basically using the higher order, the transfer functions and so on for the feedback block HS. Okay, so basically here we said closed loop zeros are obtained from GS is equal to 0. Okay? Alright. So open loop transfer function GOS defined as a ratio of feedback signal BS to the error signal ES. So if we go back, so from here to here, so what happened here is going to be GS HS, and that's what we mentioned before. Your open loop transfer function is BS divided by ES. BS divided by ES is going to be equal to GS HS. Okay, so simple to show that open loop transfer function is basically given like this. So what will be your open loop 0? Okay, so coming back, so now you can see what I've actually covered with you just now. Your open loop 0 primarily can actually be obtained. In this case here, we put things into NS divided by DS. So your open loop 0 will be NS is equal to 0. Open loop poles are DS is equal to 0. Correct? Because this is your open loop transfer function. Okay, these are your open loop transfer function. So remember, characteristic equation 1 plus GS HS is equal to 0. Open loop transfer function is GS HS. Okay, all right. So these are some of the system definition given from your lecture materials. That yes. a polynomial, what? You combine the two together because you have your GSHS. It depends on your GSHS. Alright? So if your GS, say for example, because if you remember the last round I actually show you, right? So the information given by the lecture materials a little bit not quite accurate in the sense that we mentioned here, if this is your GS, this is your HS. Okay? So last round I show you this. So I said GS can actually be broken down into your AS, BS, and HS is going to be equal to your PS, QS. Okay, so what is the closed loop transfer function? Your CS divided by RS is going to be equal to GS divided by 1 plus GS HS. Okay, so it's going to be AS divided by BS divided by 1 plus AS divided by BS times your PS divided by QS. Alright, so what happened here is you have in your closed loop characteristic equation, you can actually write it as BS QS plus AS PS, and then here is going to be AS QS. So the lecture material is not quite correct, but in the sense that if you would assume that in the feedback is always using a gain, okay? If your feedback HS is always a gain, then the lecture material is correct. Okay? If the feedback is actually a block with the pole, then the lecture material given by Glasgow is wrong. Alright? Okay? Because you can actually see that this will be your closed loop 0, which is your open loop 0 from here. So this is your open loop 0. This is your open loop pole. Okay? And this is your feedback block. So this is a feedback 0, feedback pole. Okay? So this is your feedback 0, and this is your feedback pole. So you can actually see that your feedback pole ended up as a closed loop 0. Okay, so just now the material basically we say that the feedback 0 is only AS. But actually if your HS has a pole, that pole will also end up. Because this information I give it to you in the lecture 6. Okay, so I guess when Glasgow give you their 0 is basically based on the assumption that their feedback block HS is only a pure gain. Pure gain meaning it's just a number. It doesn't have a, even if you have a function, it's just it's like your velocity feedback, right? Your velocity feedback is 1 plus KVS. So if you have a velocity feedback, is 1 plus KVS. So this is actually a block. So this block consists only of 0. It doesn't consist of a pole. Okay, it doesn't consist of a pole. So as a result, it does not violate what your lecture material actually mentioned to you, right? Your feedback, your closed loop 0 is just going to be equal to AS. But you have to bear in mind, all right? I mean, what you have learned, basically the assumption is your feedback block is a gain. That when your feedback block is not a gain, HS is not a pure gain, or not a 0, it has a pole, and that pole actually ended up in your closed loop 0. Okay, so you're going to have to bear in mind on that. Okay? Any question? Any question? I'm very worried you're looking at me like this. Yes? What's that? Oh, this is given, right? Open loop transfer function depending upon the system. So it has to be given to you. It's not that you just pluck it from the air, right? It has to be given to you. The problem has to state that this is the open loop transfer function, this is a feedback block. Okay, but what I'm trying to tell you is, in order for the Glasgow lecture materials to make sense to you, the assumption is the feedback block is just a gain or it's just a 0, like your velocity first order system, right? Like your sensor, your measurement sensor will not be a first order measurement sensor in the sense that because if your measurement sensor is a first order system, that means your Hs is going to be equal to 1 over tau s plus 1. Then whatever we discussed is wrong, okay? It will not hold. So it holds only, at most, your feedback block Hs is only 1 plus kds, okay? It will still be okay. Yeah, ns and ds is just a polynomial. There's nothing but just a polynomial only. Okay? Alright, coming back here, and then the next thing that we take a look is for this system here, you will ask, I guess I don't think I need to go through, I leave it to you to work it out because it's quite standard, right? I mean, it's just, you have a G1s, S1, S plus 2 divided by S plus 1, G2s is 1 over S, and H1s, as you can see here, 0.5s, right? I mean, he basically uses, this one is a 0. You have a 0 at the origin, 0.5s. The other one, H2 block, is 2. So you will ask to find out what is a closed loop transfer function, closed loop poles and 0, open loop transfer function, open loop poles and 0. So some of this thing we can actually answer. What is the closed loop poles and 0? Poles and 0, you need to work it out. But the 0, you do know that S equal to minus 2 is going to be your closed loop 0. Right? Correct? Agree? Because why? Because this is only 0 in this loop here. Because when you close this loop, the 0 will still stay. When you cascade it together, your G2S has no 0. So you have only one 0. And that 0 will basically stay throughout your closed loop transfer function. Okay, that 0 will stay throughout your closed loop transfer function. Maybe I just write it down. Okay, so if you to work it out, so this will be a good practice for you. I just write down what the end result Cn divided by Rs. So this is your closed loop transfer function is S plus 2. So this will be in the most generic form. Okay, so this is your closed loop 0. And then of course the closed loop poles will be basically based on this, that you need to actually work it out. Okay, so you need to actually go through in a way. But what happened here is if you were to work out, you have your, this is a closed loop transfer function. They also ask you for your open loop poles and open loop transfer function. So what will be your open loop transfer function? I think that will be the interesting thing, because what happened here is you need to actually work backward from your characteristic equation. Okay, you need to actually work backward from your characteristic equation, because if you go back, okay, so this is one of the things that you need to work on your tutorial for section 7. Okay, you need this G1S H1S plus G1S G2S H2S. Okay, so this is your equation here. Here is before you actually reach this is the end stage. Before you actually reach this stage, you actually need to cascade the original block. So you can actually see that in the original characteristic, because what is your characteristic equation? 1 plus G1S H1S plus G1s, G2s, H2s divided by 1 plus G1s, H1s. Okay, so that is your open loop transfer function. Okay, I mean this one, if you work it out based on you close the first loop, okay, you close this loop, and then you cascade it together. This loop, you close it into one block, cascade the two blocks together, and then you form it into one block, and this will be your forward path, this will be your feedback path. And if you take the two together, you basically form your open loop transfer function. Okay, but of course you can further simplify. So what I've actually shown you here, basically, the first part of it is your further simplification, because so sometimes you have to be careful, because what happened here is this basically enables you to play around. This is your characteristic equation. Okay, the characteristic equation, you can actually write it as this. You can actually work on it. Basically, it depends on how you want to work it out, right? Because this is, you can actually use this as your open loop transfer function, right? Because what happened here is you have 1 plus your open loop transfer function is going to be equal to your characteristic equation. You can also do it the other way around based on this. I can actually write it as 1 plus 1 divided by, okay, so I will also get the same thing, okay? But if you were to plot the root locus and all this and that, you can actually see that the result can be totally different. This is also possible. Alright, I take whole thing divided by this, so I got 1 plus this. Okay, and then I call this my open loop transfer function. Okay, in this case here, what happened here is I take this, I take the equation, I divide by this 1 plus G1s, H1s. So as a result, I get 1 plus G1s, G2s, H2s divided by 1 plus G1s, H1s equal to 0. So this is your characteristic equation. Okay, and this is my open loop transfer function. So you can actually see that in many ways you can actually play around. Okay, you can actually play around to actually work out what is the open loop transfer function. But nevertheless, in this case here, we go purely by the block diagram. This will be your open loop transfer function. Okay, because in one of the, I think in one of the your homework exercise that I asked you to submit for section 7, you need to actually tweak a little bit to get the k value out and so on. Because this is a case where there is no k value that you need to actually work on, but it's just basically based on what we have discussed, right? Open loop transfer functions and so on. Okay, all right. Okay, coming back to this. Okay, so we solved the. So let me know if you have any difficulty. So this is something that you need to be able to extract it out. But typically, they will not give you such a complex thing. They will give you a very simple block, and then from there you work on. Okay, very much similar to what we have. Okay, so back to this. If you remember, okay, so you can actually see that this is your characteristic equation. 1 plus fs is equal to 0. That's what we have seen it. So what we did is we call fs your open loop transfer function. Okay, kind of like, I mean, you can actually think of it as an open loop transfer function, because if that is your characteristic equation, you can actually call this fs part as an open loop transfer functions and so on. But nevertheless, you can actually write it in this format from the characteristic equation, right? Because if you were to compare this with this, so this is basically your fs. I call it the open loop transfer function, right, for simplicity. In the lecture material, they call it fs. Okay? Alright? Okay. Coming back to this, you can actually see that this is a complex rational function. Fs is a complex rational function. So as a result, I can actually write fs is equal to -1. Okay? So based on the magnitude, if I want to find the magnitude of Fs, we do know that Fs is going to be equal to 1. Correct? Okay, Fs is going to be equal to 1. But in the complex S-plane, so this is in a complex S-plane, we do know based on this result, Fs is equal to minus 1. So Fs is actually at this point here minus 1. Okay, based on your characteristic equation. So based on this characteristic equation, if Fs is actually equal to minus 1, as what we mentioned, right? Your complex number is similar to your vector. You have a magnitude, you also have a direction. Alright, you need two things to describe the complex number. You can use a real and imaginary part. You can also use your Euler representation. That means you use the magnitude plus the angle. Right, your polar form is magnitude plus angle. So in this case here, minus 1 point. Minus 1 point in your S-plane, complex S-plane. What kind of angle does it give you? 180 degrees. Okay, because this is minus 1 point, as we mentioned, the sign convention for your angle is actually counterclockwise to be positive. So minus 1 point is a fixed is a fixed 180 degrees. Okay? Alright, so two things. One is magnitude condition. Magnitude of Fs has to be equal to 1. The other one is the complex function Fs has to be 180 degrees. So 180 degrees fulfill the requirement. If you go another round plus a 360 degree, it will still fulfill the requirement, because every time you go around the circle one time, that means 180 plus 360, 540, it will fulfill the requirement. 900 will fulfill the requirement also. Okay, so for any values of your complex variable s, Fs can actually be expressed as a complex number. Okay, so that means Fs can actually be written as such: magnitude plus an angle. In this case here, magnitude is equal to 1. We have actually worked it out. Angle is basically going to be equal to 180 plus 360k. K basically depending upon how many rounds you're going to go through. So in simplicity, I can actually write it for the angle condition is 1 plus 2k multiplied by pi. Alright? Because pi is 180 degrees. So it's 2k pi. So in our characteristic equation, translating into your complex relationship, you have two requirements, two conditions that you need to fulfill. Okay, so what we are saying here is, if whatever poles that you actually work it out, if the poles is going to be your closed loop poles, it must fulfill two things: your magnitude condition and also your angle condition. Okay, you must fulfill that. That means, suffice to say that if I have to sketch your root locus, the root locus must also fulfill these two conditions: your angle condition and also your magnitude condition. Because why? Because from this characteristic equation, everything started out from the characteristic equation. 1 plus Fs is equal to 0. Because it's a complex rational function, you have your magnitude, you also have your angle condition. So you must fulfill these two conditions. That means if your closed loop poles is going to be the actual closed loop poles, the actual correct solution, it must fulfill your magnitude and you also must fulfill your angle condition. Okay? So likewise, when you go into sketching your root locus, that will be the two things that we will pay a lot of attention. Okay? Okay. So that means at all points on the root locus, we must have 1 plus Fs is equal to 0, and as a result, we must fulfill both angle and magnitude condition. Okay? Alright? So you do know this is the magnitude, this is the angle condition. But do you really need to do that all the time? You do not really need. Once you get going, okay, at the very beginning, you need to actually make use of it. The moment you get going, you don't really need to always check back, because why? The procedures that take us through the plotting of the root locus, basically, once you begin your plotting and all that, everything is okay. The rest of it, you don't have to come back and check. But you do know that anytime, at any point, if you are not sure, you should be able to make use of your both magnitude and your angle condition to check back to see whether you're on the right track. Okay? So if we go back to your Fs consists of two polynomials, right? As we mentioned, numerator and denominator, and with the gain k. And this k here is what we call your root locus gain. Okay? So k is actually the overall gain of the system. And in this case here, you have v0 and n plus u pole. So because you have n, because basically you can also have poles at the origin. I mean, in this case here, I didn't actually take into consideration of your complex conjugate, but nevertheless, I'm assuming that, you know, I mean, they all started out from the real axis and so on. They can actually start from the complex plane also. Okay? But this is basically a very generic way of putting things together. So in this case here, if we say that the magnitude is going to be equal to 1, what happened is at any one point, if this is the point on the root locus, I can actually make use of this condition to work out two things. Make sure that the magnitude is going to be equal to 1, and of course at the same time, if I am given a point on the root locus, I can actually use it to work backward to determine the k value. Correct? Because if you were to look at this equation here, if s is actually a known value, I call it s naught. So if I give you s naught on the root locus, I tell you that at this point, this is the point on the root locus. Can you give me the gain k value? The answer is yes, because all I need to do is I substitute into this fs equation. Because fs equation basically saying that all the magnitude you multiply is going to be equal to 1. So from here, I can actually work out what is my k value. Can you all follow this? Straightforward. I see someone shaking head. If your magnitude condition basically require fs equal to 1. Agree with that? Okay. So now, if your fs is actually being represented by orders. That means if you were to determine the magnitude of your fs, what are you doing? You are determining individual magnitude, your zero, your poles, and so on. Okay, so that's what we say. If you were to determine the magnitude of your fs, we are actually trying to determine the zeros and poles magnitude. If I give you a point on the root locus, that means I substitute a point s naught given, a known point, and I substitute into this expression. Okay, and we know that this condition must fulfill the magnitude condition is all the magnitude of all this is going to be equal to 1. So this becomes a known value, all this are known value. I can actually work backward to find out my k. That's what we meant. Okay, so that means what is your k? Your k basically you substitute your known value into your fs, and then you take the pole divided by the 0, you will actually obtain your k. So that is one way that you can actually use to work out what will be your magnitude if you are given a point on the root locus. So it's likewise, if you are given your gain k, you say how to find the point on the root locus. Of course, that one is a bit tedious because you need to basically make use of what? You need to basically make use of your MATLAB. Because if I give you the k, I ask you to find the point. It's actually more difficult. But if I give you the point, ask you to work backward to find the k, it's actually easier. Right? Because if I give you the gain k, that means you need to go back and solve your characteristic equation. So if it is a third order or fourth order polynomial, then you need to use MATLAB. Or else it's going to be quite tedious. Okay? So as what we mentioned, this can actually be rearranged. Once you rearrange them, you can actually work it out. And similarly, you can actually use an angle condition. Right? Based on this, okay, based on this expression here, so we will not go through the derivation, but assuming that this is the case, this is your complex function. How to find the angle condition? Angle condition, if you have a complex rational function, the angle condition is nothing more than taking the angle of all the zero, you add it up, minus all the poles angle, you sum it up together, then you minus it out. So you can actually, the beautiful thing of this is you can actually do it individual component by component. That means individual pole, individual zero. All you need to do is you sum all the zero angles, alright, with respect to the point that you were given, minus you sum all the poles with respect to the point that you are given. That means if I have to go back to use this diagram to indicate to you saying is, if I'm to tell you that this point here is on the root locus, hypothetically, I tell you that this point, I call it minus a plus jb, is on the root locus. And you should be able to basically use the angle and the magnitude condition to show that the magnitude is going to be, Fs is going to be equal to 1, okay? And then at the same time, you can also show that the angle is going to be equal to 1 plus 2k pi, okay? So if this is going to be the point on the root locus, these two conditions must be fulfilled. Okay, these two conditions must be fulfilled. One is the magnitude, the other one is basically is the angle condition. Okay, so that is what we have here. And these two relationships basically form the basis for sketching the root locus. You only need these two relationships for sketching of the root locus. But the technique for sketching the root locus is actually based on mathematical theory of polynomial. Okay, it's primarily based on the mathematical theory of polynomial, but by using just the angle and the magnitude, we can actually try to sketch the root locus. Okay, let's take a look. Alright, so as we mentioned before, if S0 is the root of characteristic equation, it also satisfies this condition. Correct? Am I correct to say that your G applying an S0, H applying an S0 is going to be equal to the magnitude is going to be equal to minus 1, is going to be equal to 1. Correct? Because basically that is your, this is basically your what? This is basically your Fs. Okay, this is your Fs. So in a way, if we were to make use of numerator polynomial and denominator polynomial, you basically, we can actually put it in a way, the G S0, H S0, the magnitude is going to be equal to K times your N S0, E S0 is equal to 1, and that's what we meant. You can actually work out the K value if you know any point on the root locus. Okay, any point on the root locus. So magnitudes are basically measured from your original open loop poles and open loop zeros to the points on the root locus. So if we go back to this, how do we actually do the measurement? So you need to actually measure the distance from here to here. This is the distance, this will be the distance, this will be the distance, because you have another point here, so this will be the distance, this will be the distance, this will be the distance. Okay, if this point is going to be, so you need to actually work it out. With respect to this point, this magnitude, so you can actually, so you don't need to pick 2 points. In this case here, if this point is on the root locus, this point will be on the root locus. So all you need to do is you check on this point. So if I have to check on this point, I do a measurement, and I do 2 measurements because I have minus 2, I got 2 open loop poles. So I need, all I need to do is, because in this system here, I have 3 poles. 1 pole at 0, 2 poles at minus 2. So I work out, so it will be a distance from here to here, and then I have 2 distance from minus 2, minus 2. Okay, so you only need to test a point if it is a complex plane, because as we mentioned, complex is always a conjugate. So if it is in is a plus j omega, then it has to be minus j omega also. Okay, all right. So this is what we have discussed. Okay, so you can actually see that the way it goes. What happened here is this is the example. All right. So let's take a look at this example to see how we can actually go about starting to plot the root locus. So in this case here, you have how many poles? You have 1, 2, 3, 4. You have 4 first order poles. You have how many zeros? You have 1 open loop 0. So this is your GSHS, the open loop transfer function. Characteristic equation is still going to be the same. 1 plus GSHS is equal to 0. So what happens here is if you were to take any point S0, so it satisfies the angle condition, then it is a root of the characteristic equation. That's what we meant, right? If it satisfies the angle condition or it satisfies the magnitude condition, it must be a point actually check it. You can actually check it graphically, or you can actually do it by angle calculation. And this is how we actually to carry out checking. So in our case here, you have 4 poles, right? You have 1, 2, 3, and 4. And then you have a 0. So you have 4 poles and 1 0. In this point, it's going to be a root of the characteristic equation, and as a result, on the root locus, that means this will be the distance, as we mentioned. If you were to draw it, okay, you can calculate the magnitude. So in this case here, if this is a point, so you have 1, 2, 3, 4, 5. Magnitude, you actually have 5 magnitudes that you need to calculate, right? So you have A1, A2, A3, A4. And you have also have B1, because B1 is actually associated with the 0. Okay? And also you have the angle. So you have angle, you got your phi 1, phi 2, 3, 4, and this is the sign, because this one is actually 0. So as what we mentioned, it's going to be using sine 1 minus phi 1, phi 2, phi 3, phi 4. Okay? Because these are all the poles. Poles are all negative angle. Zeros will be positive angle. So you can see that A1, A2, A3, A4, and B1 are the magnitudes from the poles minus Pj and the 0 minus Zi to the point SO. And then these are basically your angle. And take note that we use counterclockwise to be positive. Okay? Counterclockwise to be positive. So these are basically how we actually go about doing it. So this one is actually not in your lecture material. This actually I added on. Okay, if you have to read the, is it in the lecture? I don't think they give. They give. Do they give? This one is only in the PowerPoint. So if you were to read in your, in the section 7, I don't think it's inside section 7. Okay? Alright? So any questions so far? Any question? Okay, so you can say that if you were to find the angle of the G and H of S0, basically it's just going to be equal to the angle of your numerator minus the denominator. So what is the numerator? Numerator is resulted from the 0, so you have your sine 1, and then you minus your phi 1, phi 2, phi 3, and phi 4. So what happened here is if this point is going to be on the root locus, okay, this point S0 is this point is going to be on the root locus, you will see that the angle has to be positive 180 degrees. Cannot be minus 180 degrees, right? I mean, it can be minus 180 degrees. It can actually be plus minus, because positive 180 is the same as minus 180. So you can actually be minus 180 degrees or positive 180 degrees. But make sure that the angle must work it out to be 180 degrees. So if it's not equal to plus minus 180 degrees, what does that imply? The point is not on the root locus. That means S0 is not a solution of your characteristic equation. Okay? Then of course you do that because that is the easiest one to check. You check the magnitude condition first. Once you fulfill the magnitude condition, then you go and work out the you check the angle condition first. Once you work out the angle condition is actually plus minus 180 degrees, then you check the magnitude. Because you know why? Because the magnitude is actually much more difficult to calculate. Right? The angle is actually easy to calculate. Angle is easy to determine. Magnitude is a bit more difficult because, I mean, you need to work out the magnitude is actually a bit more tedious. So once the angle condition is fulfilled, then you check the magnitude. Then from the magnitude condition, as what we mentioned, you can actually find your K value. Okay, so you can actually see that if you were to given any point on the root locus, right, to ask you whether this is actually part of the root locus, what you need to do, you need to make use of your angle condition first. Then after that, make sure that angle condition is actually fulfilled, implying that this point is indeed on the root locus, meaning it is part of the solution of your characteristic equation. And then from there, you try to work out the magnitude condition. Using the magnitude condition, you can actually work out what will be the K value. Okay. Next week, I think we will start this. you take a look first, because what happened here is there are 8 steps which actually can be applied to plotting of your root locus, but not all the 8 steps that you will be using all the time. Sometimes you use 6, sometimes you use 7, sometimes you use 8. Okay, sometimes you use only 5, depending upon what kind of system that you're working with. But nevertheless, we will show you all the steps for you to carry out to sketch your root locus using this work example here, using this example 7.3 as an example. So what we're going to do is we will go through very systematically, step by step, what you need to do, okay, in order to sketch your root locus. Alright, so remember this afternoon, where is the attendance list? Those guys, I call out your name, I will see you in T1A 68. Right, from Alvin all the way to the guy before Louis. So you will be in T1A 68 for your lab this afternoon. So remember to bring a copy of the lab sheet. Alright, so we will try to cover this afternoon's lab. I think if you know how to use